So this is going to be different because this is a higher level class than beginning graduate students, because most of you have already had exposure to some of this stuff. But we'll try to solidify the basics and then go into more depth as we come up on things. This, I guess I should introduce myself like I do to all the students. So I'm Bruce Bugbee, and this is more for the video. And my title is Professor of Crop Physiology. Somewhere along the line, I got much more interested in the physics of plant growth than the physiology, and that means energy and mass transfer into and out of plants. And because of that, my laboratory has done well with getting funding because people want to quantify things. And many, many years ago, that led to a lot of instruments to rigorously quantify inputs and outputs. So what I've evolved to now is instrument-intensive research on plant growth. Some students have called this class, in the reviews, some students have called this class crop physics. You should just call it crop physics, because that's what it is. And that's not strictly correct, because there's a lot of biology in the class as well. What I'm going to focus on in approximately the next 8 lectures is this outline here, which I've handed out, which focuses on energy balance. It's the first part of the class, and it's the fundamentals by which we get evaporation from surfaces. As a point of introduction, and before I get way too far into this, I thought I would give you a full copy of the whole class that I teach. And you can see we're pruning off these early lectures right here. I teach this winter semesters up here, but we're pruning off this first section up here on energy balance. But this is the whole thing. And this is also the front page of the textbook I use, which is a bunch of readings of this, and I love to put all the key equations right on the front of the book so people can see those and see what's coming up. Mostly the top half of these things are the ones we're going to focus on in here. So the essence, the reason we do energy balance analysis in any field is to try and determine the temperature of objects. And anytime water is involved, now it gets way more complicated because water evaporates and changes the temperature of objects, which is why agriculture focuses on energy balance so much. If we could get a low-cost sensor that could measure the evaporation of water from a field, it would be a huge breakthrough. Just put it out there and measure the flux of water, but there isn't any low-cost ways to do that, so we do it with modeling, and lots of modeling, and we measure all the parameters around this, and what's left is this missing water, and this much water must have evaporated to balance the energy. That's the most cost-effective way to do it, and frankly, that's a big reason instrument companies are in business, because they sell instruments to measure everything. We can put plants on a lysimeter and weigh them, and that's an accurate way to get water that evaporates. But lysimeters are really expensive to install, they're expensive to operate, and only people that use those as references use lysimeters. The rest of us use calculations and modeling. We use lysimeters as well, but only for reference instruments. We can do things like eddy covariance to get water transfer, and that's expensive and requires knowledgeable people, and that's still an indirect measurement of measuring water vapor. So we keep coming back to energy balance principles to really understand where the water is going. If you type in water use in the world on the internet, you get lots of things like this. Agriculture is 70% of our water. In the United States and worldwide, it's the massive user of water. I gave a TED talk on this a few years ago, turning water into food. And the main point in that talk was people aren't wasting water. The image is if farmers are using 70% of our water, they must be just wasting it, running it down into rivers and into the groundwater. It just takes that much water to grow food. And this is one of many graphs of that. And the point is, if we could improve water use efficiency in agriculture by 1%, it'd be more than more than what you use at home. You know, forget putting bricks in your toilet and turning the water off when you brush your teeth. Those are just minuscule compared to the amount of water that it takes to grow our food, which is why it's so imperative to understand that and use every drop as efficiently as we can. We call that more crop per drop, that effort. And it takes a lot of instruments to get that analyzed, and it takes a lot of rigorous and careful theoretical development to make sure we've got it right, because so many cases are different. People need oxygen to run our respiration, and you think, what's a person's water use efficiency? What's our personal water use efficiency? And you calculate how much water do we exhale and how much food we eat. It's the reverse of plants. But people have it easy because there's 21% oxygen in the air, and we don't have to breathe very much, and therefore we don't lose much water. Plants have to work on 0.04% CO2 in the air. So for plants to breathe, they got to have their stomates wide open, and the water diffuses out into the world. I could start this by writing what I think is the most important equation in the world. And you ask people what that is, and maybe it's E equals mc squared. I mean, to me, the most important equation in the world is photosynthesis. No, there's subscripts on these C6H12, but this is the simple stoichiometry. So the plants in photosynthesis are taking this low energy gas that we use to put out fires and turning it into carbohydrate, a high energy solid. It's just amazing that they do that. And again, if this is 20.95% the oxygen, and this is 0.04% the CO2. So not only are they taking a low energy gas, but it's a trace gas. It's minuscule. Then I've said, if you took the molecules in here and turned them colors, and the nitrogen in the air, if that was, say, black and the oxygen was red, now try and see the CO2 molecules. You probably wouldn't even be able to see them. They're such a trace gas. This is 4 out of every 10,000 molecules is CO2. That's what the plants are having to work with. So they got to keep their stomates wide open to get that CO2. People can breathe with not having to exhale much water vapor because there's plenty of oxygen. As my friend and colleague Rick Allen says, it's a good thing plants don't have to go anywhere, because as soon as they start to move, they'd get out of breath. There's not enough oxygen. So of course this is going the other way. Here's photosynthesis. Here's respiration. But this low gas is really the fundamental reason we have to give so much water to plants so they can make our food. So that puts it in perspective of the stakes in this thing, trying to optimize every drop of that massive amount of water. And that's why I was honored to be able to give a TED Talk and talk about this issue of where all the water's going in agriculture. So I think to start this, I'm going to start with, get rid of some of this, another important equation, the energy balance equation. And I think I said in the outline the multiple components of this. Let's leave that up here for a minute. Let's even start before that. First law of thermodynamics, energy E in equals E out. I'm going to erase this top part here for a minute because these are different principles. So this is easily the most widely known and the most, to me, by far the most profound of the laws of thermodynamics. There's really three laws of thermodynamics. Energy has to balance. The second one is the world tends to more entropy, meaning more randomness in the world. Everything, the planets are moving apart and the world's becoming lower, more random, lower energy. And the third one has to do with absolute zero. As you get closer to absolute zero, the energy in the system approaches zero. I don't know why that law just doesn't say at absolute zero everything stops, but it doesn't. It says as you approach absolute zero you get less energy. Some British chemist said about these three laws, he said the first one you could say there's no free lunch. That's another way to say this. But he said you can't win because it's always balanced. The second law is you can't even break even because the world tends to lower entropy. And the fourth law, you can't even get out of the game. You can't quit the game. You're always at some temperature. But we're going to focus on this, energy in, energy out. So right away, if we can measure these components, we can calculate the missing components. So in the simplest sense, if this is radiation in, so for now we'll do R for radiation. Over here we have transpiration plus conduction and convection. Now these different people use different symbols for these, but I have typically used C squared, that's a 2. For conduction and convection we consider simultaneously. One's the heat going to the molecules and the molecules blown away, but they're in one term. This doesn't mathematically mean C times C, it just means there's CC, C squared. That's pretty simple. That's the essence of this whole energy balance equation. These have to balance. And why would we have whole textbooks on this thing to analyze this if it's this simple? This is reduced to the simplest components. Any good plant person is going to say, well, wait a minute, there's photosynthesis in this, and some of the energy goes into photosynthesis. And it's correct. So over here, we have P for photosynthesis, and that's some of the energy. So now we're getting a little more complicated and more detailed. Now let me stop right here and make a mention about some of the principles for this. Many books talk about this. Let me start with a different book. Pretty much every university teaches plant physiology, whether they're an agriculture, land-grant school, or anything, they teach plant physiology. Every year, new editions of new plant physiology textbooks come out. This is Zeiger one we use here. And you open up this fat treatise, it gets thicker every year. Try to find energy balance analysis in this textbook. It's not in here. That is not a traditional part of plant physiology. This deals with chemical principles and it deals with single leaves. And when it gets to calculating evapotranspiration, that's not a subject covered in this book. They do cover what causes stomates to open and close, which is a key part of this, but that's it. And they do mention water use efficiency in here, but they don't talk about covering that. But lots of other books do. And one of my favorites that I learned this stuff from, and fortunately it's now in the 4th edition, is this book by Park Nobel, Physiochemical and Environmental Plant Physiology. So the principles of what I'm talking about are in this book in chapter 7, and I use the same symbols as he does in this book, so it's a great reference for looking at the principles. Now, I brought with me a few other key books that have been important to me and also talk about these principles. One that many people are familiar with is Galen Campbell's book and John Norman, An Introduction to Environmental Biophysics. And this has got a lot of great stuff in it. It shows basic equations for this. This is also a good reference on these things. Hamlin-Jones, Plants in Microclimate, a Quantitative Approach to Environmental Plant Physiology. Anytime somebody puts quantitative approach in the title, some of the students go, yeah, I'm going to try to avoid that class. And the other students go, wow, this is cool, I've got to sign up for that. So it depends on how good people are with quantitative approaches. And here's a third one, Environmental Physiology of Plants. So this subject matter is covered in many books. It's just not covered in traditional plant physiology textbooks. So let's go back to our equation here. We're putting in photosynthesis because some of the energy goes there. Now, if we were doing energy balance analysis of ourselves, which we do, we've standing out in the sun, we've got radiation in. You got to drink water to stay hydrated. If you get hot, you lose heat by conduction and convection. Photosynthesis, for most of us, is approaching zero. I'm still working on that chlorophyll gene so I can stand out in the sun and I don't have to eat. Just have to get green skin. But our bodies are above room temperature because of respiration. So now we've got respiration in here, and in the case of plants, so do they have respiration. And when they respire, that's exothermic, that warms them up. But because respiration is adding to the heat, we really have to do something like minus respiration, because it's giving off heat, it's not using it anytime we burn up heat. So those four components are the essence of this, the four on this side. But what happens when something changes temperature? Energy in equals energy out, but this balances over long time periods. But if you take a black piece of metal and walk out in the sunlight out there and lay it out, it's going to get hotter. It's going to get hot fast, and this won't balance because it's heating up some of the energy is going in to change the temperature. Then we bring that back into the room, and it's cooling down, and we got all our 100 instruments around this thing, and the energy doesn't balance. It's cooling off because it doesn't balance. So we have to have another term over here, and that's usually called G, and that's storage. Now, storage is easy. That's either heating up or cooling off. And in the case of a leaf, and this, my analysis is going to do a single leaf now, just one leaf out there in the sun. How are we going to make the energy balance for that? We get a leaf right, and then we can go to bigger things, canopies, and all kinds of bigger things. How much goes into photosynthesis? Let's just start with a rough estimate of the size of these parameters up here. So now I'm going to ask you, how efficient is photosynthesis? Chris, you ought to know this from some classes, but what's the efficiency of photosynthesis? You can say that in the test tube, algae can be this good, in the field they're this good, but about how efficient is photosynthesis? Do you get any idea? Boston, do you know?
Not very efficient.
That's correct. It's not very danged efficient. So what does that mean? Less than 50%? Less than 20%?
I think it's in the 30 range, isn't it?
It can be, yes. Photosynthesis can be up to 30% efficient in a test tube with algae in perfect conditions. But when we go to the field, we're talking more like 5% efficiency. It obviously varies if it's how bright the light is. There's a whole bunch of factors. But let's just go with 5% here. That means 95% of the action somewhere else in this equation. So if photosynthesis is 5%, how much energy comes out in respiration? Now in people, it's energy balance in people. The food you eat, that's how much energy you get. This has to balance in food too. So if we ate 5 grams of food, we'd have 5 grams of respiration. But in plants that are growing, respiration's typically a third of photosynthesis because they're storing energy as they get bigger. So respiration might be 2%, if we can see those lined up. So now we're getting down to some terms that are pretty small here. And then storage is, in a single leaf, storage is insignificant. I'm going to see if I can draw a three-dimensional leaf here. Something like this. One of the calculations in Park Nobel's book is how much a leaf could store, how much energy a leaf could store given the magnitude of the radiation coming in. And he shows mathematically it's insignificant. A leaf is so thin, there's not much mass there, and 50% of a leaf is air. A leaf is just a bunch of cells with air in between them. So, and it's a fraction of a millimeter thick. So in a single leaf, we just ignore storage. This is absolutely not true as soon as soil enters the equation. Soil now is huge, but when we're talking about the leaves of plants, storage is insignificant, and both of these are tiny. We can easily calculate this one too, because let me draw a graph of this. Let's think about this efficiency of photosynthesis for a minute. If I draw a graph, I'm going to do this in a different color here, of photosynthesis, I love drawing XY plots, so I got a lot of XY plots. Sometimes I think I dream in XY plots. But here's radiation in, and here's 0. So it's dark, and we get up here to, let's say we get up here to 1,000 watts per meter squared. This would be typically full sunlight in a summer day. Now, normally we do this graph with just photosynthetic radiation with photons, but for these purposes, this is okay. We got energy coming in, and over here we're going to have photosynthesis. Now, here's another thing that people understand the shape of this graph at different levels. If this was a high school class, the correct answer to that question, if somebody said it looks like that, they'd probably get full credit. But what's wrong with this straight line? Why is that not full credit for a more advanced class? What does it look like? Yeah, it can't keep going. It tops out. So that part's wrong. So it tops out. So now we're up to Plant Science 301, and that's the correct answer. But it's not correct for Plant Science 501, or whatever number we're putting on this. What's still wrong about that? What if we put a plant in the dark, reagent grade darkness right here? These are not plastic plants, they're real plants. We put them in the dark, they have respiration. So we put the plant in the dark, and this is 0. It has to go somewhere down here. This line has to curve like that. Now, that line is correct at Plant Science 501. We've got this dynamic down here at 0, and we've got the flat line as a general shape of this line. When we get these 5% numbers, we're usually somewhere, I'll put this in green, we're usually somewhere on this part of the curve. Early part of the curve where we get higher photosynthesis. By the time we get out to full sun, and we're out here, now we're down to maybe 2% efficient in full sun because it just tops out. So when we say 5%, yeah, it's correct if the sun's not too bright. Here, this is the efficiency is like this, and here's 5%, and that slope of that line is more like 2%. So most of this transpiration, which is what we're ultimately after in this thing, is happening during the bright light parts of the day, and the rest of this is we can ignore it for the first order estimates of transpiration and conduction and convection. There are times when a refined analysis will include photosynthesis, but typically not. Typically, we're just dealing with this part right here, even though that's the full equation as it relates to plants. So we can put numbers on this. Quickly put numbers on this, and the sum of these two fluxes has to equal this one. So let's do a very quick calculation. And I just love back of the envelope calculations, and the goal of this class is to get everybody to where every time somebody asks a question, they go, you got some paper? And you can calculate stuff. There's all kinds of things you can calculate if you get started and get a little background. So let's say we have radiation in 1,000 watts per meter squared. Now this is a nice number to remember because right now that's about the radiation outside this classroom coming in. Let's say our leaf right here is evaporating. To be anatomically correct, water always has to be shown in blue. This leaf is evaporating enough water to stay exactly at the same temperature as the air. And this happens all the time. You put a wet dish rag on your clothesline, a black dish rag maybe to simulate a leaf, and you measure the temperature of that, it's going to be pretty close to air temperature because it's evaporating water at the same rate as the energy's coming in. And in fact, a very wet dish rag is pretty often below air temperature around here because and then as soon as it starts to dry out, now it's still evaporating water, but it goes above air temperature. So let's say it's the same. So conduction, and I got my colors wrong here. Conduction and convection is 0. And if it's the same, if this leaf is 25 degrees C and the air is 25 degrees C, that exchange is 0. So now we've really simplified this energy balance analysis to see where we're at, because we got 100 watts coming in, zeros here. How much water does it evaporate? So take off this. What you find out in this analysis is a huge part of it is just units conversion, from getting one unit to the next, getting them all straightened out, and once you get that, then I tell people a monkey could do the last part of it, just a computer can do the last part of it to get the units right. So what we want to know is transpiration, and what we know is energy coming in. So let's start by looking up, here we go, a typical number. I can put this over here. I can even zoom in. Here we go. Too much zoom in. This is out of this book right here, Utah Climate. It's published by the Climate Center, and it's just a bunch of statistics of climate. So in this example here, I have pulled out the campus weather station. This is 30-year data. This is not our new environmental observatory. This is an older station, real old, up by the place you buy ice cream up there, Nutrition and Food Science. Here's every month of the year, evapotranspiration, inches per month. Now we're going to take the highest transpiration month of the year, 7.48 inches. This is per month, and that is 0.24 inches per day. It's 0.6 centimeters a day. This is measured by, I think this is measured by pan evaporation, taking a pan with water in it and looking how much water evaporates in that pan. It's an old time-honored, simple method to do this. So pan evaporation, we get a number right here, equals 0.6 centimeters per day. So this is supposed to balance, but we don't have the units in the right order yet. So to put the units in the right order, there's one key number that you could probably have tattooed on your arm, so you could always remember this number. LHE, latent heat of evaporation. and I use this number enough I can remember it. 2.45 megajoules per liter. Now this is close to a constant. If the water's almost boiling, this is something like 2.41. And if the water's freezing, it's something like 2.49. But it's 2.45 megajoules per liter at 25 degrees C. And really this temperature doesn't matter that much. This is it's a 3 significant digits, all of them round off to 2.45. Okay, great. But neither liters nor megajoules is in this equation yet. So for this first lecture, I want to take some units and see if this is zero, if we do this conversion here. And now I'm going to erase my photosynthesis. And we're still talking about our leaf. So, 1,000 watts is coming in. Now this is a real simple physical principle, but it trips people up a lot. A watt is a rate of energy flow. So most people could probably answer on a test, a watt is a joule per second. And we just have this happen so much rates of energy, we just have this nickname for them called the watt. But it trips people up sometimes. I think the whole thing would be simpler if we always just said joules per second. But going back and forth in this is really helpful. One of the ways to help think about this is if we had a gallon of gas sitting here and you said, how many watts are in that gallon of gas? And somebody whips out their phone and they say, I'm watts in a gallon of gas. They say, I can't find it. I can't find it. If you said how much energy is in that gallon of gas, it's easy. You can find the energy in a gallon of gas out of 6 to the 10th bajillion joules of energy in a gallon of gas. Now, if I light a match and I blow it up, it is 6 bazillion watts of power because it blew up in 1 second. So watt is a rate of energy like release or energy transfer, and joules is the fundamental unit of energy. So now let's put this down here. 1,000 joules per meter squared per second. Now we're dealing with centimeters a day. I can see a conversion I need to make right away. This is the maximum rate of energy coming in the middle of the day. This one is the total water for the whole day. So over here we got seconds and over here we got days. So now I'm going to put another curve here. This is noon. Solar noon, and up here, this is 1,000 watts per meter squared, the brightest we get typically in the middle of the day. But if we're going to compare all the energy coming in a day to all the water we used in a day, we have to have the area under that curve, and when we do that, we get 30 megajoules per meter squared per day. These are a full sun summer day. 30 megajoules integrated under the curve. So for comparison, over here I'm going to change my units. Instead of 1,000 joules, 30 megajoules per day. Now we at least have the time on the same, on both axes. 0.6 centimeters of water from a pan evaporating to possibly keep this equal. Now we have to get this meters squared equal on both sides. And to do that, we're going to take a tray, a giant cookie sheet. We should sell cookie sheets and 1 meter squared cookie sheets for teaching purposes, because you could lay them out and you could put water in them. And this is 1 meter squared, our reference sheet. The radiation is coming in to that 1 meter squared. If we evaporate 0.6 centimeters of water, how many liters is that? To put the liters equal, so this is 100 centimeters. This is 100 centimeters. So 1 meter squared is 10,000 centimeters squared. 10 to the fourth. This trips people up a lot because so much stuff is 10 to the third, 10 to the third, everything's multiples of 10 to the third. This one is not. This is 10 to the fourth because it's 100 times 100. Then, remember, another reason that the metric system is so far superior to any other system, 1 centimeter cubed is 1 milliliter is 1 gram, which everybody learns that in high school. And then I do a true-false test and I say this and this is 1 milligram, and I put the milli really big and half the class misses it. It's a gram. This is a milliliter, but that's a gram. Okay, we're getting close to getting our units the same. So 1 liter is 10 times 10 to the 10, 1,000 cubic centimeters. And so 1 centimeter deep, 1 centimeter of water times 10 to the fourth centimeters of area is 10 to the fourth centimeters cubed, or 10,000 centimeters cubed, or 10,000 grams, and 10,000 milliliters. So 1 centimeter deep is 10 liters when we do this evaporation, and 0.6 centimeters per day is 6 liters. I'm going to have to erase part of my liter per meter squared per day. I went over this math pretty fast, but it's not complicated. A centimeter deep on a liter tray. If we had a liter of water and we poured it into a meter squared tray, it'd be a millimeter deep. If we had 10 liters of water and we poured it in, it'd be a centimeter deep in the tray. So 0.6 centimeters a day in a meter squared area is 6 liters of water. So we have 30 megajoules coming in per meter squared per day. Now we finally got units the same, meter squared per day, we can cancel those out. 30 megajoules in, 6 liters. Now we bring out our latent heat of evaporation, and 30 megajoules divided by 2.45 megajoules, mega, capital M, per liter. and I think this comes out to about 12. I'm going to put about here because it's real close. 12 liters per meter squared per day. This is how much water would have to evaporate to keep this thing at the exact same temperature as the air. And what happened in this calculation, when we measure this, we only get 6 liters. Now I'm going to wind up on this principle because tomorrow we'll pick it up from here. If this was all that was going on, you would then write in your notebooks, well, clearly the object got hot because it doesn't balance. It needed to evaporate 12 liters of water to keep itself at air temperature, and it only evaporated, these plants only evaporated 6. It doesn't balance. This cannot be 0. It heats up. And you would be correct in the analysis of this, but it's more complicated than that. This is only shortwave radiation in. This was a very simple analysis. This assumed every watt of this was absorbed, and some of this gets reflected. Some gets transmitted. And this is only shortwave radiation. We have to calculate longwave radiation to do a comprehensive analysis. So I've filled up the board, but tomorrow we'll break down this radiation into its component parts to see how much of that radiation actually got absorbed. If we put, and here's a perfect example. We do pan evaporation, right, to get these numbers. Just put a pan out, measure the water evaporating at time honored. What if the tray is made out of aluminum foil and another tray is painted flat black? Huge difference in evaporation from those two. So we got to account for the different amounts of radiation absorbed in order to make this balance. But this is an empirical number, 0.6 centimeters a day during the hottest month of the year around here. And we can, once we get this number analyzed, then we can start to look at partitioning between how hot the object gets and how much water it has to evaporate. This is largely driven, well, it's driven by just the temperature difference. So we can measure the temperature difference of this, and then we start to zero in on transpiration, which, like I said, we don't have any good instruments to measure that directly. But this was an example of some simple units to get to this. Now, I'd like to end sometimes with a homework assignment, which I'll just tell you the homework assignments in here, and you can decide if you want to work them. But so I said this whole thing is units conversion. Is that close enough? Can you read that? Here's a homework assignment. Sometimes I've given this on the first day of class. So Einstein's, it's one of the top 5 most important equations in the world, E equals mc squared. How much energy is in 1 pea seed, if this is right? And how long could you live if you just ate 1 pea seed? And you could use all the energy in that pea seed. And of course, c squared, the speed of light squared, is a huge number, so it's a lot of energy. But this is about the simplest equation you can get, and now think about units conversion. So get the energy in a pea seed from the typical weight of a pea, and this, because mc squared with SI units and SI unit conversion comes out to be joules of energy in the pea seed. I'll show you the key for this tomorrow if you want to, but the key for this is setting it up with the units and looking at this, which I'm not going to quite stop yet, which brings me to, particularly if I can find the handout of this. Here. All of you know SI units. Here's a nice symbol for the whole world. And SI units are, of course, wonderfully simple, 7 base units. And these calculations get immensely easier to get them down. As you could see from this example, getting them down to base units so we can compare different things. Nowadays you can look these up on the internet, not just the base units, but all the relationships, and most of them are so simple, like watt and joules per second, you remember them. But here's a little handout that I've found useful on this for some of the relationships. This is a two-sided handout, and it helps to understand the relationships. Now, when we talk about energy balance, we're only talking about a very small subset of all the units in here, but it helps to be fluent in the simplest relationships of SI units, and this is something I found that's useful. I got a second one that I found useful, and that just looks like this. The first one's double-sided. It's got some units on the back, but this is just conversions among units. Every single beginning chemistry book has these SI units in the front. And sometimes I think people see those and they go, yeah, good, and then they can forget about them for years and years. And then you get to an energy balance analysis and you get to remember them and use them. So I'm going to stop here, and we'll pick this up tomorrow. Now, what's that? Oops. Did I? I must have not hit double-sided in the copy machine. All those are one side? Yeah. And it's the meters. We need to copy the second side. Ooh. This is even worse, because this one has the same thing on both sides. This is really wild. Wait a minute. This is all 7 units. There's no 2 sides. It's one side. I said 2 sides because I was looking at the other. No, I'm wrong. It does have 2 sides. It just takes a subset of the units. It does have 2 sides. The first side is self-sufficient, and the next side is a subset of these with some of the more common ones. We can copy this, and I can give you the second side tomorrow. Any questions? How to apply this?
So, point number 2 on this handout indicates the 7 components of the energy balance. Are you splitting conduction and convection to be 2?
No.
What's the 7th
No.
term?
For the purposes of the class, I'm going to introduce the 7th term tomorrow. In a nutshell, it's splitting radiation into short and long wave.
That was going to be my next question.
Which,
it's not splitting conduction and convection, if it's splitting radiation.
Yep. But I like to start with the simplest thing and then get more complex. And this is, to work this out in 5 or 8 minutes and see how to finally get it in the same units, that's the essence of energy balance. And then you get to where, okay, it doesn't balance. Now, why not? And are our instruments not calibrated? And the answer in this particular case is the model's not complex enough yet to account for that. So it's a model needs to be more detailed to account for it. As a rule of thumb, well-watered plants stay very close to air temperature. So this term for well-watered plants is always small. And if we get all the radiation right, and this is exactly air temperature, then we know transpiration. But we got to do short and long wave both to get that term right. As soon as they run out of water, of course, imagine a cactus in the desert. One of my students came back and he said, it's 100, they were in Phoenix last week, and they said, I can't see how people, man, they go from one building as quick as they possible to the next air-conditioned building. It was 115 in the day, but it cooled off to 90 at night. And they're, how far is my car? Can I make it? You know, and man. But imagine a cactus without water. The tissues of that cactus are just astronomically hot. And it just sits there, and the cactus is almost no transpiration in the middle of the summer. So now we can run this the other way. What if T was 0? Now we run this analysis for putting a metal hammer outside in the sun, let it get to equilibrium. Now try and pick up the hammer. And it's so hot you can't pick it up because this is an enormous number and this one's 0. So on the timing, I'm thinking if we do every day this week, that's 5 lectures, we could, I put 8 lectures. But when I look at what I've done, typically it's maybe more like 6 or 7 lectures to get to because usually I give a pretty long lecture in the beginning about how I'm going to grade the class and stuff like that, and you can just skip all that. So we could do this whole thing by the end of the week, maybe. Let's see how we're at, how we go. Particularly today I tried to do, I don't know how long was that? Yeah, and that was including the introductory stuff that we might edit out, but I mean, I'm going to try and do 1 hour of stuff. But if I did an hour and a half, or we did some and we stopped and took a little break, you know, we could get done by the end of the week. But if we get into more details and there's more questions, well, then it'll take longer, but that's good. And I'll try to weave into this the instruments we use. Everything's a component of the whole thing. There's no single instrument to measure what we want to know. We just surround it with indirect instruments and basically calculate it by subtraction, which is how we do everything. And if we can measure something easily, then we just measure it. But there's a whole bunch of stuff that we can't measure, so we have to model it. And transpiration is one that's subject of all kinds of models. All right, I'll stop there.